Right, page 290 to 291, you had 17 to 27, the odd questions, and then just for good measure, number 28 as well. Let's go and take a look at those several questions that you had to answer. Excellent. All right. Number 17 is a long answer. What are the 6 cases of image formation by a concave mirror? Let's just take these one case at a time. Give us the first 2 cases. Kendall.
The first case is when the object is an infinite distance away, but the point image is at the focal point. Okay, good. And then a real image is produced.
Okay. And the second case?
The real image will be inverted.
Okay, but where's the object that produces a real image, that produces, where's the object?
The center.
Behind the center of curvature, you get what kind of image?
A real image that's inverted.
That's inverted, and anyone else have an extra detail in case 2?
Reduced.
It's reduced as well. All right, case 3, Michael.
Case 3 produces real same-size images that are inverted.
Okay, if the object is where? Case 3, it all determines, the case depends on where is the object.
In front of C.
Case 3 would be if the object is at C, and then it produces the unmagnified inverted real image. Case 4, the object is now
in front of C,
but still behind the focal point.
It produces real enlarged inverted images.
Good, real inverted enlarged. Case 5 is a weird one, Audrey.
No image.
Because if the object is where?
It reaches the focal point.
Good. If the object is at the focal point, you get no image at all. And then case 6.
You get an upright virtual image behind the mirror.
And it is enlarged or reduced?
Enlarged.
Enlarged. And this is when the object is?
Behind the mirror.
Well, the image is behind the mirror. The object has to be in front of the mirror.
Yeah.
Where is the object, though? Okay, the placement of the object was critical in these different cases. We'll go over it again, but the object is in front of the focal point. All right, number 19. Describe the image formed by a convex mirror, Kendall.
The image formed by a convex mirror is a virtual upright and reduced image that's closer to the mirror.
Good, virtual upright reduced image closer to the mirror. That's for all convex mirrors. Number 21. What feature of a parabolic mirror leads to many practical applications? Michael.
The clear focusing ability of parabolic mirrors makes it useful in many practical applications.
Good, a very clear focus. We're going to talk about that today. Number 23, what is the mirror equation, and identify each variable, Audrey?
The mirror equation is 1 over f, which is the focal length, equals 1 over d sub o, which is object distance, plus 1 over d sub I, which is image distance.
Very good. Number 25, define lateral magnification, Kendall.
Lateral magnification is when the image is enlarged or reduced in relation to the object.
Okay, in relation to the object, I would take that, I suppose. That's not what I was looking for, but it's not wrong either. Michael, what did you have for 25?
Lateral magnification is the enlargement or reduction of an object's distance.
Audrey, what did you have?
I had similar to Kendall, except I said it's symbolized as capital M equals h sub I over h sub o.
Yes, defined as the ratio of the image's height to the object's height. That's lateral magnification. Let's see, number 27. Can magnification ever be less than 0? And if so, what does this indicate about the image? We're back to Kendall.
Magnification can be less than 0 and it becomes inverted.
Good. And negative magnification, which would be less than 0, indicates an inverted image. And number 28, what does a negative height indicate about an image? Michael?
Negative height means the image is flipped.
Good. Or the word we would use is inverted, which also, by the way, would mean it's real. Now, those last few questions, we're going to get into that math after spring break. Okay, so we're going to wrap up the rest of it here today. Go ahead and turn back, if you would, in your textbooks to page 85, 285. Back to page 285. And we're talking about spherical mirrors, 2 types of spherical mirrors. Michael?
Convex and concave.
Convex and concave, which one's which, Audrey?
The concave is the one that caves in, and which the reflectance part is on the inside.
Good. Concave, the reflecting surface is on the inside.
Then convex is when it bulges out and the reflectance is on the outside.
Good. Reflecting surface on the outside for convex. We said that for a spherical mirror, the center of the mirror's surface, class, is called the vertex. The center of the sphere is called the center of curvature. Remember on the ray diagram, you had the vertex in the middle of the curve. The center of curvature was the dot out here. Halfway in between was another dot. What was that dot, class? The focal point. If I talk about how big the mirror opens, either the distance across the mirror or the angle that the ends of the mirror would make back to the center of curvature, class.
Angle of curvature. No.
It's called the amount, the opening amount,
Aperture.
the aperture of the mirror. The distance from the center to any point on the mirror, but most easily measured by the vertex, from center to vertex, that length is called the radius of curvature, or radii of curvature would be all those distances. They'd all be the same. For that line though that goes through C and V, we refer to that line as being the principal axis. We use those in those sketches we would draw. What do we call those sketches, class? Ray diagrams. On the ray diagram, we use three principal rays. One of them is the
central ray.
How do we draw it?
Draw it through the center of curvature to the mirror, and then it bounces back through focal point.
No, through the center of curvature to the mirror, and then right back again. Because remember, if you go through the center of curvature, you're traveling along the radius, which is already the normal to the tangent. Another principal ray.
Focal.
How do we draw that?
It goes through from the top of the image through the focal point and then bounces parallel.
Good. Reflects parallel after passing through the focal point and hitting the mirror. And then the last ray, Kendall?
Parallel ray.
Parallel ray, how do we draw it?
Parallel.
To that line thingy.
That line, yep.
That Audrey said was called the Audrey? Principal axis. Okay, so Kendall, with the parallel ray is parallel to the, and then once it hits the mirror, it's going to reflect. Class? Through the focal point. Again, theoretically, Kendall, all parallel rays would reflect to the focal point. That's why we call it the focal point. We'll talk a little bit more about that in just a second. The cases of image formation, let's review. If the object is an infinite distance away, infinite of course, what do we get? A little, we call it a point image. A little dot of light, a point image. Where would it be? At the focal point. That's why it's the focal point. That's where the light focuses. For an object that's an infinite distance away, it would have to be some kind of light source. We get what, class? Point image at the focal point. If the object, any object now, is closer than infinite distance, but it's still further away than the center of curvature, we no longer just get an infinitely tiny little dot, class, we now get an image that's actually produced. Describe the image. It's inverted. It's reduced. And it's, well, inverted means flipped. So it's inverted, it's reduced, and it's real. It really reflects off the mirror. And the object continues to come closer, what happens to the image? It gets bigger until if the object reaches the center of curvature. Describe the image now. It's now unmagnified, but it is still real and inverted. If the object is now in front of the center of curvature, again, that image is continuing to get bigger. It's also continuing to move further away from the mirror, isn't it? So if the object pushes now in front of the center of curvature, now the image will be magnified, or enlarged is the better word, because magnification could be negative, or it could be small. So it's enlarged, it's still inverted, and still real. It continues to be, it's a real dot of light, it's a real reduced image, it's a real unmagnified image, it's a real enlarged image, until finally the object gets all the way to the focal point. And at the focal point, class, nada, just blurriness, right? Remember seeing the blurriness on the videos yesterday as the ball went back and forth, or as his face went back and forth, right? Part of it too is you saw the blurriness most of the edges of the mirror because the angular aperture was so great, and we're going to talk about that in just a second. I don't want to get ahead of myself. If the object now goes in front of the focal point, though, what's produced? A virtual image that's upright and enlarged, right? And so the key then, by the way, with making the cosmetic mirror is to make sure that the curvature of the mirror has a big enough radius that when a lady holds it, she's not going to have her face at the focal point, right? Typically, you'd hold it, what, about a foot away from your face when you're holding the mirror? Well, that means you'd want the focal length to be, say, 2 feet, which means you'd want the radius of curvature to be, say, 4 feet. So you want your curvature, and by the way, what that does is when you take just a piece of it, and the curvature is so slight, you don't even notice it. That's why with your magnifying mirror, you don't really notice that it's curved because it's got such a big radius of curvature. Again, you don't want it to be one of those where you hold it up like, where is it? Oh, there I am. You don't want to have to hold it that close. So again, math goes into all of that. Make sure you know cases of image formation. All right, make sure we know those cases. It's concave. Everything yesterday was concave, right? And concave images have lots of different possibilities. What about convex mirrors? Next thing in your notes. Under cases of image formation, now we deal with convex. And there's only one case, which is nice. Convex mirrors can only do one thing. Convex mirrors always do the same thing. Think about where you maybe see convex mirrors. Where would you see a convex mirror commonly?
In playgrounds.
Okay, that's true. On playgrounds, they'll sometimes have convex mirrors. Or distorted mirrors more often than not.
Cameras.
Oh, that's true. Let me think about security cameras. It's kind of like a mirror because it's that smoked glass. It's like a mirror. But even like stores like Target and drugstores and stuff, they'll oftentimes have those mirrors as well, like just an actual mirror, no camera associated with it. And when you look in the mirror, where does the image appear to be? Inside the mirror, right? And what else do you notice about everything you're seeing in the mirror? It is a panoramic view because everything is so small. Is stuff upside down? That'd be really hard for an employee to use, right? The point of it is that an employee standing in one spot can see like 3 or 4 aisles worth and make sure people aren't like taking stuff and sticking it in their pockets and stuff, right? They often have those. Well, nowadays cameras are so easy to use that less and less used. Like Walmart has little cameras everywhere throughout the store, particularly in the cosmetic areas and such. But those mirrors, everything is made smaller, everything is upright, and everything is virtual, appears to be inside the mirror. This is also true, for instance, of not the driver's side mirror on the car, but the passenger side mirror. You ever notice what it says at the bottom?
Things are closer than they appear.
Object and mirror are closer than they appear. That's because you have a slightly convex mirror. Not enough to distort the shape too much, but so that on your blind side, it shows you a lot more of what's over there. So it is able to shrink everything just a little bit and therefore able to show you a wider panorama, so to speak. Not as much as the store mirror, but still a bit of a panorama. At the school I went to, we had a bus parking lot where they would drop off the kids and then park the buses. But there was a bus drive that was kind of a curvy drive, I guess to keep bus drivers from just racing in, hot rodding it or whatever in their, 53-foot long, whatever. Anyway, and so there was, right at the corner, there was a great big tree with a big old convex mirror sitting there. So that way, as you were getting ready to pull out, you could see if anybody was coming up that drive because it was 1 lane wide. And so if somebody was already coming and you decided to come, you're both sitting there wondering, now what? Okay, so they had that mirror sitting there. Again, it shrinks everything down. So write this down for concave mirrors. They always produce virtual, upright, reduced images. Always virtual, upright, reduced images. Think about it this way. The curvature being on the outside, right, that reflecting surface on the outside is always going to reflect rays away from the mirror, right? Which means rays can't converge, really. They have to theoretically converge inside. So that's the reason why they always form those images, which again is helpful, right? If you got inverted images, that's really hard to drive. It is smaller, right? That's why I say they're closer than they appear. What looks one size in this mirror would look smaller in the other one, so you get the illusion of something's further away. Those are convex mirrors, questions on convex mirror. Now, you see a term that you need to write down in your notes there on page 286, spherical aberration. Spherical aberration. An aberration, you might remember that term maybe from, I think it's Macbeth. I think Lady Macbeth sees a ghost, and Shakespeare refers to her as an aberration. All right, a ghostly figure, if you will. Well, spherical aberration is this phenomenon caused by mirrors that are too big, so to speak. Light rays won't all perfectly hit the focal point. The book mentions this: if the angular aperture is 10 degrees or less, okay, so we're talking either a really small mirror or a really big radius of curvature, so the angle isn't very big, you'll get a really clear focal point. But most mirrors have a bigger angular aperture than that, so the light rays out on the outside don't hit the focal point perfectly. Most of the light, though, comes to the focal point, so instead of getting a clear, bright point of light, you get kind of a fuzzy bright spot, this ghostly bright spot, so to speak. I think that's where the term aberration comes from. Spherical, meaning it's caused by a spherical mirror. So spherical aberration is the fuzzy bright spot formed near the focus, or I guess you could say it's the imperfectly focused light, would be another way to phrase it. Okay, the kind of fuzzy bright spot or imperfectly focused light, caused by an angular aperture that is too large. It's caused by an angular aperture that is too large, and I've referenced it a number of times already. That angular aperture is important, and again, light rays won't perfectly focus. And so as a result, you don't get a clear, bright pinpoint of light. You get a fuzzy bright spot. We call this class spherical aberration. Now, what if you needed a perfectly clear focus? Well, you wouldn't use a spherical mirror or use a really small angular aperture. There's a better way. We're going to talk about it in pre-calculus after spring break. We're going to start talking about parabolas. A parabola in general has a perfect focal point. We've kind of referenced this in pre-cal already. But for a parabola, there is a point called a focal point, and there's a line out in space called the directrix, getting a little ahead of ourselves in pre-cal. But the parabola is defined as a locus of points that are equidistant, and it's not perfectly drawn, you can tell, here and here. The distance to this point, this line, the distance to this point is the same, and because of the nature of a parabolic curve, anything coming in parallel would reflect perfectly to that focal point. So jot this down in your notes: a parabolic mirror has a perfectly clear focal point. A parabolic mirror has a perfectly clear focal point. So if you needed a perfect focus, you wouldn't use a spherical mirror, you'd use a parabolic mirror. The book uses the example of a reflecting telescope, uses a parabolic mirror. You understand the stars are so far away, right, that what you'd want to do is collect as many light rays as they could possibly give to you that can travel through space. So you'd use a parabolic mirror. Now again, a parabola could be really tight like this, or a parabola can be really wide like that. You remember in Algebra 2, Kendall, how by changing the A value of the quadratic, we would either shrink it in or widen it out. Well, if you used a very, very, very tiny fraction, you would really flatten that parabola out, but it would still be a parabola, which means light rays coming from afar would still focus perfectly at a point. The book kind of gives a picture of what this might look like. You've got these light rays coming in from a distant star, or maybe the moon, or whatever you're looking at. As the light rays come and they hit the parabolic mirror, no matter where they hit, they'll all reflect perfectly to the focal point. Well, they would perhaps place a mirror en route to this focal point that would reflect these light rays up to a lens. We'll talk about lenses later, how lenses flip images, but you could get that image then projected to you. So that would be one example of using that parabolic mirror. More often than not, though, you wouldn't use a mirror so much for the mirror's sake, though again we'll look at an example, but more as a reflector to redirect light. For instance, headlights in the car don't actually have circular, spherical backings behind the light bulb. They have parabolic curves. And the parabolic curve can redirect the light. A mag light. Ever played with a mag light? Turn the little knob, and what does it do? It widens or shrinks the beam. Spotlights at movie theaters or athletic events and things like this. Spotlights, have you ever noticed the beam widening and narrowing? Well, that's using a parabolic reflector in the back. You have the light source, and the parabolic reflector reflects the light back out. Aim the light at the reflector actually redirects the light. So different placements with a parabolic reflector. So let's just say we have, it's technically called a circular paraboloid. Cut it in a cross section this way, you get a parabola. Cut it this way, you get a circle. And so in 3 dimensions, I'll show it in 2. If you put the light perfectly at the focal point, but technically something this type of focus would be in here, put it perfectly at the focal point. If light rays coming in parallel would reflect to the focus, then a light source at the focus would reflect all of its light rays perfectly parallel, wouldn't it? So if you wanted a perfect, nice beam of light the exact same width as your spotlight, you'd simply adjust the turn it, which basically slides the mirror in and out. As the mirror turns in and out, when you get the light source to be at the focal point, you get perfectly parallel beams coming out. Well, what if you were to redirect the focus in even closer? You'd actually produce somewhat of a pinpoint effect. You could focus the light really well. Or if you were to put the light source further out, you get kind of a floodlight effect. And so you could widen the beam. So parabolic reflectors are used headlights, mag lights, spotlights, searchlights, those things where you can change the width of the beam. That's using a parabolic reflector in the back. Something else that's kind of interesting, we're going to watch a video. There's a video on the in the description of this one that actually talks about how we could use parabolic mirrors to produce electricity. You know, we produce electricity right now with coal. You burn the coal. Coal produces fire. Fire produces heat. Heat boils water. Boiled water produces steam. Steam drives turbines. Turbines turning produces energy. Right? You do the same thing with nuclear energy as well. Nuclear energy is a little bit different. Water energy turns a wheel. Turning wheel produces energy. Right? We could do the same with light. If you could capture sunlight with a parabolic reflector and aim that light to perfectly focus at a water vessel of some kind, the water vessel could produce steam, turns turbine, produces electricity. So it's something they're looking into. It's a new take on solar power, not with solar cells, but with which have to be replaced, and the discarded waste is expensive and all that stuff, but actually producing that. Or one of the newer things then is to produce a water pipe and run a water pipe right through where the focal point is. That way the mirror can stay perfectly still or turn with the sun. But if the water pipe passes through, all of the light rays focus on the water pipe. Water pipe gets boiling hot, water's boiling, boiling water produces steam, and same thing in effect as well. So, anyway, parabolic mirrors, a lot of really cool applications, but it's because what's true of the parabolic mirror, class? The perfect focal point. The spherical mirrors don't have that. Again, in theory, yes, light rays from an infinite source come and they focus at the focal point if the angular aperture is not too big. Most of the light rays will still probably focus around there anyway, but a parabolic mirror captures all the light and reflects it to the focus, or use it on the flip side, use it as a reflector to reflect light outward where you want it and direct it that way. Questions on the parabolic mirrors? All right, well, we're going to go ahead and end the lesson here. I want to show you a video again. If you're watching in the description, look in the description of the video, and we'll see that video. It's a little bit of a longer one for you to watch, but I think it'll be really, really insightful. Coming up in our next lesson, there's no written homework, but coming up in our next lesson, we will have a quiz over these 2 sections, the introduction to reflection of light. So I'll be preparing for that quiz in our next lesson. And then also in the next lesson, we'll begin looking at the math of mirrors.